No, it's fine.
So, starting off this video with the grinding of a pencil sharpener. But that's excellent. I just lost all my subscribers, thanks. So guys, what questions do we have on homework? We were talking about logarithmic functions. It's all right, keep going. It's fine.
Are you writing homework or are you writing
The homework.
Okay.
33 to 39. So
Don't you mean 21 to 39? Oh, you're just talking about what part you want to do.
wow, you guys are doing excellent things for me, for my videos, sharpening pencils. So here we go. So 33 to 39, we'll take a look at here. So most of these, it's easiest to evaluate these without a calculator if you are translating them into exponential form. All right, so let's take a look at 33. So log base 125 of 5. So first of all, what is that asking us?
125 to what power is 5?
Correct. So 125 to what power is 5? And I could translate this. So if I just say my answer, just give it a variable name, I could do that. And I could translate this into exponential form, which will kind of look exactly the same as what we just asked. So this means 125 to what power is 5? Man, I'm getting a little bit of lag there, but that's okay. A little bit of lag. So, let me cut that. There we go. Might improve. So to figure this out, 125 and 5 are related. They are both powers of 5. This is 5 to the first. 125, I don't know if you realize this, is 5 to the third. So 5 to the third, all to the x equals 5, right? So 5 to the 3x equals 5 to the first. So this is a very algebraic approach you could have. You probably could have answered the question right off of your verbal statement that we made, but and now I've got two powers that are equal. Their bases are the same, so their exponents must be equal. So therefore, 3x equals 1 and x equals 1/3. All right? But you could have also gotten this just saying 125 to what power is 5, and you might have realized, oh, the cubed root of 125 is 5. Cubed root is the same as a 1/3 power. Right?
We have no idea
Then,
what the exponent
Or like,
well, then eventually we could do it this way a little bit, which will more systematically give us the answer if I can write both of those in terms of the same base. But we will eventually want to try to become really familiar with how, right, negative exponents affect things, how fractional exponents affect things, and just
Like
know some of these numbers. Yep.
I have no idea what the
Yeah.
square
Yeah, 37 giving a decimal answer. Well, actually, no. This one maybe we can do. Let's take a look at it. Log base of 49 of 343 equals some unknown value. I'm adding that myself. So let's translate this into exponential form. So this means, well, let's do the verbal piece first. 49 to what power is 343? All right, so that's not completely obvious. So 49 to the x is equal to 343. Now both of these are actually powers of 7. 49 is 7 squared. And 343, I believe, is 7 cubed.
And how was I supposed to know that?
Well,
because Halo is filled with 7s and 343
I didn't know that one. 117, yeah.
Polar 1 has 14 letters.
Interesting. So now I've got two bases that are the same, therefore their exponents must be the same, so 2x equals 3, or x equals 3/2, or 1.5 if you're a fan of decimals. Right?
So what happens if I don't know the squares or the cubes of everything?
Figure it out.
Yeah, I mean, you could do a little bit of calculator work, like if you'd probably recognize 49 is 7 squared, and then I would have tried to start figuring out, is 343 also some multiple of 7? So I'd have done, 49 times 7, and I would have realized one more exponent would have gotten me there. So yeah, 343, maybe not completely obvious to us, but that's all right.
39.
39. Okay, so log of the square root of 8. Yeah, for instance, I doubt I would know these ones. Oh, sorry. Base square root of 8 of 4096.
The 8 looks kind of like a 4.
Yeah, it does there. That's better. Or good enough, anyway. So let's translate this into exponential form. So that's the square root of 8 to the xth power is equal to 4096. Okay, I think I got this one. Square root of 8. I could write that as, I'll do this slowly, 8 to the 1/2 x. Square root is the same as a 1/2 exponent, right? And 8 is, both 8 and 4096 are powers of 2, so that's what I'm starting to lean towards. 8 is 2 to what power? Right, so 2 to the 3rd, all to the 1/2 x. I'll just keep working on this side. So this is the same as 2 to the 3/2 x. Whew, tricky. Now 4096, I believe, is 2 to the,
12.
is it 14 or 12? Yeah.
It is 1024 is 10.
Right, and then double it, and then double it. Yeah, so 2 more, so 12, yep. I agree. So 2 to the 12th, 2 to the 12th, 2 to the 12th. And now if I've got two powers that are equal, their base is the same, therefore their exponents must be the same as well. So 3/2 x equals 12. So this is a little bit trickier than I'd intended. I didn't show us this quite this way yesterday. So multiply both of those by 2/3. And I would get x equals 8.
Yeah, what I did was I just reduced it down to, I just reduced 4096 to 8 to the 4th.
Oh, yeah, there you go too. So in this case, that happens to also be 8 to the 4th, right? So you could have never converted them both into that. And actually, I mean, that makes sense. 8, let's see, 2 to the 3rd, all to the 4th, right, is the same as 2 to the 12th. So that's why 8 to the 4th right there. So yeah, so I like that approach as well. Technically simpler. My gut instinct is always to reduce it to the smallest prime number that I can, I guess. Or base. Yeah, I guess base. Because, yeah, it doesn't necessarily have to be prime. But unless I was doing prime factorizations. But yeah, in that case, that would be more insightful and would have saved us even a little bit more work. It would have at least, well, no, I'd still would have had the fractional exponent. Other questions on the homework?
I was actually digging this one.
Digging it? Can you feel it, Mr. Krabs? Can you feel it? So, all right then. So I guess what we can do is continue with lesson. Do some solving. I'm tempted. I could just fit this right on this page, but that's just like some homework review. I'll open a new one. Let's see. File, save as. So yeah, unfortunately these videos will have far more little downtime and intermission, but still would be helpful nonetheless for some individuals. Let's see, so homework, and what was that, page 4? New? 722, right? Or 723, my bad. Here we go, save that, and open up a new screen. So continuing yesterday's notes is what we will do. So you can fold your homework if you want, or you can do that later.
You give me a sec to put my
It's the only
homework in my
four.
folder.
Yep. All right, so here's our new screen. I'll have to figure out how to do like those little timestamps on YouTube videos, so I can just be like, at 10 minutes and 31 seconds, that's when the lesson starts, so then people could just like skip right to those. But I don't feel like it. Let's see, so we are doing logarithmic functions continued from yesterday. So I think what we'll work on now,
This will have 4 or 11.
we are still in 11.4. Oh, so I'm going to breeze through some properties of logarithms. That's good. That's good stuff. So now, logarithms, as we indicated earlier, are the inverse of exponential functions. And the properties of logarithms are going to be similar to our properties of exponents. They're going to have some themes, I guess, that kind of exist throughout. So let's see. I think I'll do the properties in green. So properties of logs. Props of logs. So let's see. Let's do log of a product. So, getting some lag. Come on, computadora. Log, let's see, I might as well be consistent. Log base b of m times n. All right. Technically, I don't need these parentheses, but I'm just, wow, I'm getting serious lag here. Serious. So if I've got the log of a product, all right, that is going to equal the sum of 2 logs. All right?
That's 6 or B.
Those are base b. Sorry. So the log of a product is the sum of 2 logs. That, I would say, is symmetric to the product of powers property, right? Or if I multiply 2 things of the same base, I could add the exponents. Notice I'm multiplying 2 things within the same log, so I can add logs. So a little bit of a parallel multiplication kind of became addition a little bit.
And for probability. And is multiplication.
And then ors. That's a little bit more abstract than that. That doesn't fully relate. But so let's see. Let's just verify this. Let's do a quick little example. So let's do log base 2 of, and let's do 4 times 16. All right. So according to this property, now I could just multiply those and solve this another way, which we'll use as a check in a moment. But according to this property, that should be the same as log base 2 of 4 plus log base 2 of 16, right? And log base 2 of 4, what does that ask us?
2.
And what is the answer to that?
2.
2. And log base 2 of 16, what does that ask us? 2 to what power is 16? And that would be 4.
6.
So I end up getting 6. Which, notice, is the same thing I would have gotten if I had done this. I guess I'll call this my check.
64.
Right? If I did log base 2 of 64, 2 to the 6th power is 64.
Why can't we just do it like that?
Because sometimes we'll want to know these properties, especially when we don't know some of the values. So if, for instance, that 4 was an x, I wouldn't know, I wouldn't be able to simplify it any further.
X times 16 equals 6. Would that be?
Wait, I'm sorry, what was your question?
So, like, log base 2 of x times 16 equals 6.
Well, then we'll eventually get into solving equations where you'd solve for that x. And we'd have to use some of these properties to work our way backwards. So that's why we won't be using just this method. I'm just kind of verifying these properties for you, so you've got a little bit of buy-in, I guess. So let's look at another property. So here we go. Let's do quotient. So log base b of m over n. So based on the symmetry that these have with properties of exponents, what do you suspect I would get? Right, yeah, I'll subtract. So that'll be log base b of m minus log base b of n. All right? So the log of a quotient is the difference of two logs. When I was in college, I had a professor who would always do little verbal statements like that just to really get your mind set on the concept.
I'm going to go home and the title of this is going to be Property of Logs, so my parents are going to be like, what?
Yeah,
Why?
it's true. Actually, when I taught this in Math 3 this semester, I ended up playing the Ren and Stimpy video where they sing about logs. It's pretty good.
I know some properties of logs. They're round, they're heavy, and wood.
Yes, in fact, they are. So let's do a quick little example of this. So let's do log of 5. And let's do 1 over 125. So 5 to what power is that? Perhaps we could just figure it out. But let's break this apart into two separate situations here. So according to this property, what does this become?
Log 5 base 5 1 minus log base 5 125.
Yeah. I apologize that my 1 and my L are identical. That looks like that's the absolute value of OG sub 5. Is there...
Og 5.
Wait. Is there a element of OG5? G doesn't... I don't think... Yeah. I don't know why.
Oh, gee, there's 5 problems.
Yeah. Yeah. So it's the absolute value of the compound O quint G or whatever it would be. I don't know. Oxygen. Too bad. They should have just used G for gold. But I guess when they were probably naming the elements, periodic table, they weren't in English. Yeah, AU for gold. Oh, well.
And what's platinum? It's like
I don't remember. I don't remember them all. So log base 5 of 1. 5 to what power is 1?
0.
Oh, it's all right. It's all right. We tricked you there. Let's see. 5 to what power is 125? 3. What is 0 minus 3? Negative 3. Huh. Let's do a check this way this time. Is 5 to the negative third power? What is that equal to? 5 to the negative third. That's 1 over 5 to the third, which is 1 over 125. That's a tiny 3 right there.
That's a 3?
Yeah, 5 to the...
No, it's like sideways mini art.
Yeah, sure. Sure. So that property's not that bad. Good stuff, good times. So that is the quotient. I guess I'll throw some names on these. This is the product property of logs. This is the quotient property of logs. Quotiente. Oh, power property. This guy
Hang on.
is powerful.
Multiplication.
What? What?
It's like with exponents and like
Well,
when you multiply the exponents, it's adding. When you
Yeah.
divide them, it's subtracting. And then it's power and power.
so check this out. This is really crazy.
M to the n.
They'll use the letter P, I think, is usually what I've seen. Yeah.
Oh.
Now this one is this property in itself is what allows us to solve equations that have x or have a variable in an exponent. All right, this is going to be big time powerful here. So what do you think I do with this? I agree that it'll be some sort of multiplication that would be symmetric with the power property of power, power to power, right?
Log base b of m times log base b of
No, not quite. This will actually just be p times log base b of m. And in case there's any confusion as to where this p is being applied, the p is being applied to just the m. It's not the whole log being raised to the p power. P.
power of p.
Imagine that, like, if someone was named Peef, like Keef. Is Keef I-E or E-I? Really? It can be either?
I don't know. I think it's E. I think it's E.
Whatever. I before E, except after Keef. I don't know.
I before E except in Keith.
Except in Keith. So here's the power property of logarithms. Let's see if I can think of a quick example for this one. I might just steal one here. Nah, that's not that interesting. So what if I've got log base, let me do one that actually we could do. 2 of 2 to the... did you guys write that 2 yet?
No, to the 2. To the 2.
No, I want to make it a little more interesting.
No, you should have been like.
Man, that's like stairs right there. Doot, 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 doot.
You should have been like 1 to the 2.
So let's apply this property.
No, like what?
Base 1 and base of 1.
So I can swoop this 3 out front and make this into multiplication. So this becomes 3 times log base 2 of 2. And what is log base 2 of 2?
1.
1. So 3 times 1 is 3.
So, really.
Or if you had used the exponent and done that, it would have been log base 2 of 8, which is also 3.
Right, so 2 to the third is 8. And actually, it's kind of funny. So 2 to what power is 8 would be 3. And I mean, that's kind of like, it's kind of like almost a redundant question when it's in this form. 2 to what power is 2 to the third?
3.
Oh, the third power.
Yeah. But is that basically
It's kind of
the
amusing.
same, or is that just a coincidence?
No, those would always be the same. Yeah.
So it's only just going to be this power.
Yeah.
So
If it's
Yeah.
if the base is the same thing.
Oh yeah, 2 to 1 power.
Let's see. Then here's a good one. They call this the power of equality.
Powers.
The power of equality.
Yeah. If I was like running for president, my whole campaign would be, can't everyone just be treated equal? Imagine what the power of equality would do for our country. But then I would like suddenly pull out a math property and I'd start teaching, and they'd be like, what? I don't understand.
And all the math nerds would laugh.
Yeah.
For an MIT.
It'd be excellent. So let's see. So this one's kind of a conditional statement. If log base b of m is equal to log base b of n,
M equals N.
then m equals n.
Oh.
And that's symmetric to the power property that I've been using but not naming. Here, I'll let you guys finish writing that. The power of equality. Wow.
So something on the line where someone figured out how to make 2 equal to 1.
By subtracting 1.
How?
Like it was like the end of the formula was 2 equal to 1. But it involved dividing by 0.
Oh, okay. Interesting. Let's see. Oh, no, I don't have those there anymore. But, because that was on the previous slide. But earlier on in this video, when we were going over the homework, and I had like, I can't even think of an example, but when I had like 2 to the 3 equals 2 to the x, and I said if the two powers are equal and their bases are the same, then their exponents are equal. Notice the symmetry to this property. If I have 2 logs that are equal and their bases are the same, then their ofs would be equal. I don't know how to describe that any better. Their ofs, right? Log base b of m. It's the of in that logarithm, right? So m equals n. So that property is going to actually allow us to solve things. So let's do an example of that. So let's say if log base 8 of 3x minus 4 is equal to log base 8 of 5x plus 2. Then what would be true? Then 3x minus 4 equals 5x plus 2. And I guess that's, well, now let's solve it. Let's go all the way. Go all the way. Yeah, I'm getting close to the bottom of my page as well here. So let's see. Negative 6 equals...
No, it's negative.
X equals negative 3. Let me do a check here. Log base 8, I was almost going to write a 3. 3 times negative 3 minus 4. Is that in fact equal to log base 8 of 5 times negative 3 plus 2? Log 8 of negative 9 minus 4.
Negative 13.
Blah.
Negative 15 plus 2.
And then what's that? Negative 15 plus 2. I don't feel like writing log base 8 over and over and over again. I don't know about you guys. But I'll get log 8 of that. Log base 8.
Log8.
You only ended up not writing it once.
Yeah, but think about all the time that I saved by not writing that.
About 2 seconds.
And we just spent that time, but I was resting. So,
It's all good.
I'll go back and write it.
You just wasted that time.
Let's see. Actually, and then this isn't a property so much, but a matter of notation. But I just want to point out log base 10 of whatever is the same as log of whatever. All right. So if I'm working in base 10, you don't have to write the base. And that's when I had a student state the famous fact that 10 is the Hobbit in the land of logs. Do we know what that student meant by that?
Yeah.
Why is 10 the Hobbit in the land of logs? Because 1 is the Hobbit in the land of like multiplication, right? Where multiplying by 1, it's implied, it's invisible, it's a Hobbit wearing a ring. So here, if you don't see a base written, and it's log of something, there's an invisible 10, like a Hobbit wearing a ring, right?
That's what my calculator was doing, because I put log of like 125, and it gave me a number before I even put something on the
Right, exactly. And that's what, so your calculator works in only 2 formats. I guess I'll throw this other one up here. Log base E of M is the same as ln of M.
E is like 2.
Are we going to need to know that to write that one down?
Yeah, that's the ugliest ln that I've ever written. But ln on your actual calculator, there's actually an ln button, which we'll be using eventually later on in this chapter. Let's see. So yeah, here's my log button, right? So when I do that, that's in base 10. Here's ln. So that is the same as log base E. You guys don't know what E is yet?
Oh, look at the
We'll tell you
shift.
later.
It's the natural numbers.
What about the shift?
It's 10 to the x and then e to the x.
Right, 10 to the x and e to the x. So those are actually, so 10 to the x is the inverse of log, and e to the x is the inverse of ln, right? Which ln is actually referred to as the natural logarithm.
What is so special about
Because
E?
isn't E the natural
What is so
number?
special about pi? Or I?
Well, pi is used for
Pi is
E
the
like
ratio
a natural
between.
number.
Pi is the
E
ratio-
is a number. Yeah, E is the natural number. It's also called Euler's number. EULER. Euler. All right. And yeah, it's a number that's found within nature, so that's why it's called the natural number.
2.7 something.
Well, if I do second shift on that button, oh, I'm not on. Here we go. So second E to the, and if I raise it to the first power, there's an estimate for that number. Which, by the way, that number is irrational, even though it appears to have that repeating pattern of 1828, 1828. It is not, in fact, repeating. Okay.
It just is for that sequence.
Right. Yeah.
So what does E do anyway?
We'll do a whole lesson on that later, but
But for now, we don't have to worry about it.
no, I just wanted to let you know that. So, so Ellen's right, or mysterious student that I did not name on the internet, that I used an alias for, right? You don't know who I'm speaking of? Yes. That if you were to calculate log of 125 on your calculator, that is 10 to that power is 125. That's not in base 5 that maybe we would have intended. And actually, just to verify, 10 to 2.09. What did I do?
There's two. You didn't put anything in.
That would do it. All right, so there's log base 125. So 10
Answer.
to the second answer. Oh, what did I do? I hit second entry. How embarrassing. How embarrassing. Which also I could just hit second shift log to get the 10 to the right away. If that really saved us time, I don't know. So 10 to the second answer, and watch this. 10 to that power, that crazy decimal, happens to be exactly 125.
So why is 10 the Hobbit in the land of logs?
Because it's invisible.
Because it's invisible. There's an
I know.
invisible 10 right
I
here.
know. I mean, what's special about 10 that makes it invisible?
Because if you see a logarithm that doesn't have a base, it's a
Well, I mean, why did they do it like that?
Well, because we work in a number system of base 10, where every 10 digits you count and then increases in the second placeholder, right?
Or base 2.7182818.
Right. We could,
They work in base.
counting in base
Hang
E,
on,
I
let
think
me
would
go
be
get
weird.
another piece of paper.
Yep, gladly. So yeah, so mathematicians just decided that working in base 10 as their standard base would be the easiest, especially because you can do a whole lot of work with scientific notation in this, right, where I'll have stuff like 10 to the negative 8th power or 10 to the negative 23rd power if I'm talking about moles. No, 10 to the 23rd power is moles, right, 6.28. No, or is it 2.3? Well, anyways. But yeah, scientific notation, base 10 system, that's why they chose to use 10 to be the Hobbit in the land of logs.
Yeah, they should have chosen 73 to be the Hobbit. It's the Chuck Norris of numbers.
Can I run to Nichols' office for 2 seconds to give him the
Or a
paper
2-minute break.
Could, what about that?
For like 2 seconds.
But what about this?
On the chair.
Can you do that during a 2-minute break in a moment?
That was ridiculous.
In a moment? Let's see. Solve log base P of 64 to the 1/3 equals 1/2. Yuckies. Log base P of 64 to the 1/3 equals 1/2.
So log base P of 64 over 3 equals 1/2.
No, that's 2.
Well, there's a couple ways we could do this, but let's try. Sometimes when solving, it will be helpful to rewrite stuff in exponential form. So, what does this mean in exponential form?
E to the half equals 64 to the third.
P to the half, right? The base to this is equal to that.
E to the half equals 4.
I could technically use some of my other properties and whatever first. I could have moved that 1/3 out front, things like that. What is 64 to the 1/3 the same as? How'd you get that? Did you divide 64 by 3? Is that what that means?
No.
No.
If it is, then
Wah,
divide
wah,
it really
wah.
Right, that's the cubed root of 64, which is in fact 4. Oh, my 1/2 just switched over to a 1/3 there, didn't it?
We're doing that.
And then how would I solve for p? You could square both sides, or you could imagine that the 1/2 power is the square root, so to undo a square root, you square, whichever way you think about it. So I would get p is equal to 16. All right? So that's not bad. Let's do one more example on solving. Then we'll get some partner work in here. Okay, so this is, I'm jumping the gun here and getting into a crazy problem right off the bat. But these problems are awesome. Oh, yes. A little bit. But your familiarity with logarithms will be helpful. I do actually want to get into, we'll see. I might, we'll see. I at least want to get through this. So let's see. So if I want to solve this.
11 of x squared plus x equals 6.
X squared plus x?
Yep.
Where'd that come from?
Well, when you're adding logs, it's the same as multiplying.
Okay. Why are you wanting to combine those logs?
To make it easier, because I know the answer to that.
Well, let's see. The reason we'd want to combine logs is not that one. Where is it? Right here. If I can get this to be one log equal to another log, I can just drop the logs from both sides and just equate their insides, right? So that's going to be my general approach. Is
So it's log 11.
right. Write each side as a single log. All right, is my general approach here in this case. So, and you are correct that the sum of two logs is the same as the log of the product. I'll write it out like this for now.
Is it 1 and 11?
Thank you. Yeah, that is 1 and not 11. There we go. And so now I've got the log of this is equal to the log of that. The base is the same, so therefore their insides must be the same. So x times x plus 1 is equal to 6. And now what should I do?
X squared plus x equals 6.
But it's already factored. Isn't it nice having it factored?
No.
No. Why is it not nice having this factored?
Because we have that same.
Because it's not equal to 0, right?
Unless you want to subtract 6.
Well, but then it's not entirely factored if I subtract 6. So yeah, that's why I want to multiply this out. And I'm going to move this 6 over here at the same time, like that. Right? I'll show that work if you'd like. I'll say minus 6, minus 6. There we go. Yeah, true. So now what would I do to solve this? Or what would you do to solve it?
Wow.
What could we do? Easier than that. It's related. Easier than AC method, although AC method would still work for us.
Would you take out an x?
Nope, because that would bring me back to this. I've got a quadratic set equal to 0. I could use quadratic formula. I could solve by factoring. AC method is a possibility. But this is actually easier because I've got the positive 1 leading coefficient there. I could fast factors, or quick factor. And then I've also got, I could use completing the square, but I wouldn't want to solve by completing the square. Why? Because of the odd value of b, I would end up having some fractions in the work, and I don't know. You wouldn't be wrong for solving by completing the square. It's just,
Oh,
Yeah.
I think I know how we
think
can.
we should do
I
the
think I know how we
quadratic
can
one.
get factors out of just this.
How would we do that?
-2 and +3.
All right, so I'd find the factors of 6 that subtract to be 1. So 1 and 6 have a difference of 5. 2 and 3 have a difference of 1. So I'll have an x with a 2, an x with a 3 equals 0. And the signs are different because they multiplied to be negative, and the more influential one must be positive. And now I've got two factors equal to 0. This we love. X minus 2 equals 0, or x plus 3 equals 0. So x equals 2, or x equals -3. Quadratic would have been more work, I'd say, in that case. That's true.
What happened to sung that song?
Say what?
Now-
Say, Mr. Wadi, how about you try to sing the quadratic formula song while we all sing Yankee Doodle?
That would not be helpful.
Or we could say,
But now,
Just, just
question.
for the heck of it, see how hard it is.
These answers are not necessarily legitimate answers. It's possible. Now, it turns out, it turns out, back when we talked about logarithms, let's see, does it say here? Let's see, the logarithmic function y equals log base a of x, where a is greater than 0, all right? So, and a is not equal to 1. So your base has to be positive and not 1. And let's see, is the inverse of the exponential function, blah, 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 if and only if x is equal to a to the y. Now, it turns out, similarly, if I look at the graph of a logarithmic, let's see, I've got one right here. We talked about the domain of this logarithmic graph the other day. Here's my green function as a logarithm. What is the domain for that?
It's you flip the X to the Y thing, right?
Well, but what's the possible x values for this green function here?
Infinite.
Everything?
Anything that's bigger than 0.
Anything bigger than 0, right? Because I have no x values that are negative there. And it turns out because of that, the inside of your logarithm, the of part, you can't input a negative number because it's not part of the domain of a log. All right? I was thinking it was going to say it up here, but I didn't spot it there. But yeah, so it turns out
So
that I can't take the log of a negative. So -3, if I do log base 11 of -3, that's wrong. And even here, if I did -3 plus 1 is -2, it's the log of a negative, would not work. So it turns out that -3 is extraneous. Now, that doesn't mean you can't have a negative answer. Because what if,
Well, we have
ignoring this, what if I had x equals -0.5, right? -0.5 plus 1 is still positive, right? So maybe it combines with something before I take the log that would still give me a positive outcome, right? So extraneous, I guess I'll leave that there. There we go. So it turns out I only have one solution that works, right? And 2 works because 2 is positive there, 2 plus 1 is positive there. I could actually go through and do a full check, but I won't do that for now. So anyway, so there's some properties of logarithms. There's how to solve logarithmic equations. I think we are good for now, and we'll do some partner work in a moment.